Over the years, reinforcement learning has achieved impressive tasks using simple rewards. However, it takes millions of samples to train. Batched data collection has greatly accelerated learning. However, vision-based tasks still train for hours or days despite using heuristics to simplify the RL problem. A reason behind RL's inefficiency is that it only interacts with the simulation through scalar reward signals. It treats the simulator as a black box. Instead of RL, we use backpropagation through time with differentiable simulation. A good case study is vision-based obstacle avoidance. First, you simulate the robot on policy. Now, during the backward pass, you analytically propagate information through each state you've encountered, updating the policy based on what it saw at that time. We used BPTT to train a robot to walk around obstacles using depth inputs in minutes. Check out Mujoko's GitHub for part of our implementation. Here's our overall architecture. First, let's isolate the blind locomotion part and solve it using BPTT. To propagate reward signals to the feet, we specify target positions from the Rayburn heuristic. Unfortunately, BPTT converges to front flipping. We hypothesize that BPTT is converging to a local minima due to a noisy loss landscape. This brings us to our first contribution of applying BPTT to the paradigm of residual policy learning, where we hot start the learning process to a deep loss valley. Our policy begins as in-place trotting, trained by imitating simple kinematics. This lets us escape the local minima and learn a high-quality gait. This paradigm also works for higher velocity targets. But was BPTT really necessary here? While it's more sample efficient than RL ends up getting higher asymptotic rewards. Going back to the final policy, we isolate the vision problem by abstracting the robot as a ball. Here we find that BPTT excels over RL. Instead of the body, we penalize collision based on where the body is expected to be. This teaches the policy to associate depth images to the upcoming obstacle much earlier in advance. While PPO fails to converge even after 150 million samples, BPTT learns a viable policy after only 100,000 steps, taking seconds on a GPU. Our method works just as well for other obstacles such as walls. Now, let's put it all together. We jointly learn locomotion and navigation as a residual over the frozen trotting anchor policy. The anchor actions and proprioceptive observations are processed in a dedicated subnetwork. We then flatten the depth image and feed it along with the state embeddings through another subnetwork. Our setup learns a reasonable pixel-to-joint angle policy for end-to-end navigation and locomotion in minutes. Our locomotion policy is robust to out-of-training distribution perturbations. The vision component also manages to safely operate with untrained image noise. See our paper to find out more.